Good afternoon, everyone. So this is the final thesis presentation of Miss Kyrien Janeena Tabucan. Her thesis is entitled Effects of Halloysite Nanotubes, or HNT, on the cadmium 2 plus adsorption capacity of a cellulose acetate thin film membrane.
So, with water pollution being quite rampant, especially with heavy metals found in wastewater, separation processes come into play. Now, the most notable ones so far are reverse osmosis, solvent extraction, chemical precipitation, and adsorption. Now, this is why polymeric membranes have been playing a very significant role in water waste treatment. So, why cellulose acetate and why HNT? So, CA has been established to be a biodegradable synthetic material, and it is inexpensive because it is very abundant in nature and it's a renewable source. It has a renewable source. Its surface charge is slightly negative, and its surface is hydrophilic. It's also porous and non-toxic. So, aside from being biodegradable and non-toxic, it's also non-toxic. So, it's actually good for the environment. Halloysite nanotube, on the other hand, is actually an aluminosilicate, so it's comprised mostly of aluminums, silicons, and hydrogens. And HNTs are actually in the nanometric scale, so this means it has it's quite rich in terms of surface area because it is, of course, it is in the nanoscale, and it has a highly negative surface charge, and it is low cost due to its availability and in nature. So we disperse the HNT nanoclay in a beaker filled with NMP, and we stir that solution for about 20 minutes with a speed of 450 RPMs, or rotations per minute. Now, before we added the pellets, we did ensure that the HNT was evenly dispersed and the solution was now homogenized. So we added the CA gradually, not directly, not the entire bulk amount of CA for that corresponding membrane, simply because if we add it entirely, it would just clump up together and it would not it would not mix evenly. So it was important to add it gradually. So we made sure to add little by little CA pellets every 15 minutes. And we stir the entire solution for about 6 hours with the same speed, 450 RPM. And then we stored all of them in a vial before we casted them. So the nanocomposite thin films were made again via NIPS process, and we just use a casting knife to transform it into a thin film membrane. So we poured the CaHNT solution onto a clean glass plate, which was washed with distilled water. And then as we poured it, we ran the casting knife through it with a 60 micron setting. And then we submerged that entire glass plate into distilled water up until the thin film has detached from the glass plate. Now, this was to ensure that the remaining solvents were able to evaporate and dissociate from the membrane. The thin films were then air dried and stored for characterizational tests. So for our heavy metal adsorption experiment, we needed to produce a 10 ppm solution, but our source for cadmium ion solution was actually 1000 ppm. So we took 10 ml of a 1000 ppm cadmium solution and mix that 10 ml with 990 milliliters of distilled water. It is important to use distilled water in this context because we do not want traces of magnesium, chlorine, or calcium, which can be present if we use tap water. Now, as we combine the 10 milliliters of 1000 ppm cadmium ion solution with 990 milliliters of distilled water, it yielded a 10 ppm solution. We allotted 90 milliliters per sample, so there's 30 milliliters per 2-hour mark. So there's 2, 4, and 6 hours. So what we did was we submerged that 1 by 1 centimeter of thin film membrane inside the beaker with a 90 milliliter solution. And it was placed inside a water bath with a maintained temperature of 25 degrees Celsius and stirring every 15 minutes. So after 2 hours, we took 30 milliliters worth of aliquot and stored that for our 2-hour mark sample. And we did the same thing for 4 hours and 6 hours. So for this magnification, pure CA presents to be the smoothest of all the membranes, while adding 5.5% HNT actually led to a rougher membrane. You can see quite a bit of texture. Adding 1% HNT actually led to a smoother membrane compared to figure B. So figure C here is smoother than figure B, but figure C is still rougher than figure A in terms of how it looks at this magnification and with the texture present on the surface of the membrane. In figure D, you can see there's an increased amount of texture, and this is actually where you can start to see, even if it's just a 2D image, you can already foresee that it has an uneven surface. So at this concentration, you can already see, even if it's a 2D image, there's already an uneven surface forming. And for sample E and F, where there's 3% and 5% HNT, there's a massive increase in that unevenness. There's more texture present. And so overall, it's actually sample F with 5% HNT, which is the roughest membrane if we base it on the SEM images alone. For the AFM images, you can see, well, let's first look at sample A here, which is pure CA. So pure CA is not completely smooth if you look at it in itself, if you don't compare it to the other membranes. But for the sake of context, comparing it to all the other nanocomposite membranes, it is relatively the smoothest. But if you look closely at the peak, so when I say peaks, those are the white regions and valleys are the darker regions. So the peaks, if you look closely at the peaks, you can actually see that there's tinier peaks and valleys within that big peak. And so what this means is at the nano level, because these images are 5 by 5 microns. So this is at the micron level. So at the nano level, there could be so much more peaks and valleys that we can see for a pure CA membrane. But at this level, only the bigger ones are actually evident. So we can see here that the surface of each peak and valley of the pure CA membrane is not completely smooth. There's indications of small peaks and valleys within it, but relative to the other membranes, it is the smoothest. Now, moving on to 0.5% of HNT added to the CA membrane, we look at figure B here. So figure B, it has more peaks and valleys compared to figure A. But if you notice, if you look closely at each peak and each valley, it actually presents as a smooth surface. Now, looking at figure C, there's more peaks and valleys, but this time when you look closely at each peak and valley, there's actually tinier peaks and valleys within that larger region. But as we increase the concentration to 1.5% HNT, you have here in figure D, the frequency of peaks and valleys, which was supposed to be high from sample C, when it came to sample D, there's actually a decrease in frequencies. There's fewer peaks, there's fewer valleys. But if you look closely, the peaks and valleys of sample D is actually rougher than the peaks and valleys of sample B. For sample E and sample F, which has 3% and 5%, they both manifested an increase of peaks and valleys in terms of their frequency, in terms of their number, as well as the texture of each peaks and valleys. Because if you do notice, when you look closely to sample E and F, each peak and each valley contains even tinier peaks and valleys. So for pure CA, as I've mentioned earlier, it was the smoothest relative to the other membranes. Now, it made sense that it yielded the lowest adsorption capacity. Now, for 0.5%, there's a significant increase compared to pure CA due to the peaks and valleys. So what happens is when there's peaks and valleys, the fluid from our heavy metal aqueous solution can be entrapped there. And once that fluid is trapped within each valley, there's better retention time for our cadmium ions to actually interact and adhere to our membrane surface. For 1% and 1.5%, so you can see here in 1.5%, there's actually a rise in the frequency of peaks and valleys. And for 1.5% here, there's a decrease. So as you can see, if you compare the adsorption capacity of 1% and 1.5%, the orange and the yellow lines here, 1% clearly had a higher adsorption capacity compared to that of 1.5%. So even if 1.5% did have a higher amount of HNT, but based on the surface morphology, 1.5% HNT yielded a membrane that had lesser frequencies or lesser number of peaks and valleys. So of course, with our 1% HNT, because it has more valleys, there's more area for our fluid to be retained, for it to be entrapped. Therefore, there's more chances of cadmium ions being trapped as well and adhering to the surface of the membrane. Now let's focus on the quality of each peak and valley. So we have established that the adsorption capacity does increase if there's more peaks and valleys present. But if each peak and each valley would have even tinier peaks and valley within it, then it would actually increase our adsorption capacity. Now, why is that? Because if we look at a bigger valley and we have entrapped fluid there, the bigger the valley, the more fluid trapped there is. And if there's more peaks and valleys within that bigger valley, then there's more fluid that can be retained. So that increases our retention time. If we increase our retention time, we actually give the cadmium ions more chance or more time to adhere better to the surface of the membrane. So it's better if it's a high frequency or a high number of peaks and valleys inside a bigger valley, because if it's inside a bigger valley, it is not as affected by Brownian motion or other motions, say steering the aqueous solution. Because of course, if it's just peaks and valleys on an even surface, like as you can see previously here in sample 1%, because of that, it's actually very prone to being affected by the Brownian motion, the rapid motion and the rapid random and erratic behavior of water molecules. So that might disrupt the adherence of the heavy metal ions to our membrane. But with 3% and 5%, you can actually see that each peak and each valley has a rougher surface. And so this indicates that it will increase the retention time because it does prevent it from being affected by all these external forces, leading to longer retention time and better adsorption capacity.